All right, so today what we're going to talk about are parent functions. So we did Algebra 1 review, which was primarily linear functions. What do you guys know about linear functions? Focusing on the graphs. What do we know about linear functions with regards to the graphs? Anybody? It's a straight line. So a linear function has a straight line, right? So it's just a straight line, all right? Now, absolute value functions, this is an absolute value function. What do you notice about the absolute value functions? It's two straight lines, but it's V-shaped. So this is a line. And then quadratics, this is a very fancy, it's a curve, but does anybody remember what those are called? It's parabolic or parabola, but it's just U-shaped. So there's a fancy word called parabolic, but you could think of it as being U-shaped. And so what we're going to talk about are the different functions. Now a constant, the constant, and I kind of glossed over that, that's a horizontal line, and that's like y equals 2, y equals 1, horizontal. Boy, I totally messed that word up. Horizontal. And so that looks like y equals 1. Well, let's talk about the domain and range. So the domain, there are really only a couple of times that you have what we call a domain restriction. We can't take a negative square root, and you can't have 0 in the denominator. So probably 99% of all functions, for their domain, it will be all real numbers. And you'll see Mr. Adams write it down like this sometimes, R with an extra slash. That just means that all real numbers. In other words, you could put any number in for x, right? Domain is referring to the x values. All right, so domain is referring to the x's. Range is referring to the y's. And so based on the shape of the functions, the range depends on the function itself. So for a horizontal line, the range is equal to the function. So this is saying the function is equal to 1. Now, just to kind of remind you guys about function notation, remember that a function is, you have an x value, which we call an input. And that's associated with the domain. So all the possible x values that we could plug in for the input is the domain. That goes into some sort of mathematical formula that we can call a function. And then it spits out what we call an output. And that's usually a y value, okay? And that is associated with the range. So that's the connection on all those. Now, functions are very specific types of mathematical rules or expressions. Basically, there's one unique output for each input. Okay. But the domain is also what we call the independent variable. Now, the reason this one's called independent is because the other one depends on this. So this one over here, your y value, is what we call the dependent variable. I'm writing stuff down and I'm looking out, and you guys aren't writing this down. You need to write this down, please. I know you're enthralled with my teaching, but make sure you write all this stuff down. And so based on the nature of this, so we say that the function is f, and sometimes we'll say g, but it's a function of x. So we're used to seeing things like y equals, so let me back up, I'll write it over here. For example, we just did a bunch of work with linear functions where we said y equals mx plus b. But if we write that in function notation, we would say the y value, which is a function of x, is equal to m times x plus b. Okay? So function notation identifies that equation as a very specific type of equation that we call a function. Now this should all be reviewed from Algebra 1, but it's been a while, so we'll go over it. Okay? Now parent functions, the way that we use this in the real world, there are linear things that happen. For example, a linear function is your growth. Did you know that a pediatrician can predict how tall you'll be as an adult based on how tall you are when you go to your 2-year-old physical checkup, right? So when you see your pediatrician when you're 2 years old, they have a chart, and you basically double your height. So when you're 2 years old, whatever your height is then, you basically multiply it by 2, and that's about how tall you'll be when you're an adult. And it's just mathematics. What they did is the pediatricians measured kids how tall they were when they were 1, how tall they were, or long actually, how long they are when they're 2, how tall they are when they're adults. And they went back and they said, the height of these kids as adults are about double what they are when they are 2-year-olds. And so they come up with, it's a linear thing, right? You grow at a constant rate, believe it or not. We talk about growth spurts, but on average, over the long haul, it's basically a linear function. That stops at some point, but you just grow, and that's how they guess, okay? And so in the real world, we use this math or model or data, and we look at it and we go, man, I collect a bunch of data. It looks like a straight line. Maybe I can make a linear equation to help me predict some things. Or I collect data like the stock market. A price goes down and then it goes up, right? If I were selling winter coats in the Midwest, and this is January, well, I'm going to sell a bunch of them here, but as we get closer to June and July, I'm not going to sell as many. And then as it starts to get colder, I'm going to sell more winter coats. So there's this behavior that if I collect the data, the numbers, how many coats that I sell, it's going to go up and it's going to go down. And when we look at the data, it looks like one of these shapes. And then what we do as mathematicians is we go, okay, how can I write an equation? But the first step in that process is identifying what type of shape the data fits, okay? Does everybody have this written down? Let's move on to the next. This is like example 1. And so I'm going to zoom in on this. I want you guys to write this down. This is the function. This is the function of x that is 2 times the absolute value of x plus 1. So if I think about this in my function model, this is my x input, right? It goes into this equation, which is 2 times the absolute value of x plus 1, and then it kicks out an output, which is y. Okay? And we call this equation a function, lowercase f. Okay? And so my y value, my input, is really the value of the function evaluated at whatever I plug in for x. Okay? And so let's look at this in terms of some of these values. So a function, if I have an input of x, which, by the way, you guys need to make sure you're writing all of this down. My x is my input, which is the domain. My y is the output, which is the range, right? And that's domain. So this is the input, and this is the output. Also, this is the independent variable, and this is the dependent. Okay? So then, if I plug in a value here, When x equals -1, this point right here, this is x equals -1, comma, 3, right? That's what that value is. All right. So what does that mean? Well, if I say x equals -1, and I plug that into my function, really what I want is 2 times the absolute value of -1 plus 1. So what is the absolute value of -1? Just +1. Well, what is 2 times 1? 2 plus 1 equals 3. So for all the values of x that I plug into this function, when I plug in 0, I'm going to get 1. When I plug in 1, right, I'm going to get +3. And so that's all these points right here. And that's based on the mathematical relationship between those. But what do you notice about this? Well, it's V-shaped. Okay. Well, the parent function so it's absolute value, right? It's an absolute value function because we said that it's V-shaped. But what else do we notice about that? Well, what is the domain? Well, as I mentioned before, the domain is almost always going to be all real numbers unless you see a fraction. And sometimes mathematicians say all reals. Mathematicians don't like to write a lot of stuff down, so we have all these shortcuts and phrases we say. But that just means all real numbers. Now, the range is a little trickier. The range is all the possible y values. So usually you think in terms of the lowest y value and the maximum y value, the minimum y value and the maximum y value. So when you look at the graph, what's the lowest the y value will be in terms of y? Well, this point right here is the lowest point on the graph, which is actually 0, 1. And then all the other y values are greater than that, so you would say that y is greater than or equal to 1. That is the actual range for that function. Okay? So then there's a transformation that takes place. Now, I'm going to show you the transformation. I just want to make sure that you guys have all got this written down because the transformation is how we shape the functions or these equations to fit the data. So then let's look at this in Desmos real quick. So I'm going to come in here. And so the parent function is y equals the absolute value of x. Oops. And there's the parent function, okay? And I'm going to type this in a little fancy. I'm going to say the absolute value function of a times the absolute, whoops. So I'm going to add the slider for a, absolute value of x, and then I'm going to say plus b, and I'm going to add a slider for b. So right now, if I put b at 0, this is the parent function, okay? Notice that that blue line is right on top of that red line. Do you guys see that? Well, our transformed function is 2 times the absolute value of x plus 1. So if I come back here and I change a is going to be 2. So watch what happens when I change that to 2. See what it does there? It just takes the v and closes it a little bit. Okay? Technically what it does is it stretches it vertically. And I want you to think about that. The original y values are going to be multiplied by a factor of 2. So those y values will increase quicker. That's why it's like a vertical stretch. okay? Now, this B is really like a vertical shift, right? And technically, we would use A and H, but I put B. This is usually referred to as H. But if I go and change that to 1, what it does is it shifts it up, okay? So that's the difference between the two functions. I'm going to take a little quick screenshot of that, and we're going to graph that. And so that's what we're going to be doing when we identify parent functions and transformations. So in the real world, I have data that looks like this blue line, right? Looks just like this blue line. I recognize that it's probably an absolute value function. And then I have to know where to put the numbers to change the shape of it, right? So I have to look at it and I go, okay, I want to change the shape of it. That's going to go in front of the absolute value function. I want to shift it up or down. That goes outside of the absolute value function. So just real quick, if I change this vertical shift, it goes like this, right? And we'll dive deep into those in a little bit, but this is just the first example, okay? So I might have some data, and then also if I want to open that up, I can open this up this way, like that. So that's what those values will do, A and B. Now you can do something like this on the inside and say minus, well technically that would be H. And I add the slider there, and this does a horizontal shift. So when I change this, it does this. And so that's what we're going to work on is transformations, okay? Does that make sense? Technically this would be K, and so we'll add K and delete B. And so this is the transformation of the parent function. So if I line this up and let K equal 0, and let H equal 0, and let A equal 1, that's the parent function. And then if I have a bunch of data, I could change that parent function however I see fit, moving it left to right to fit the actual data or values. So when you look at something like the stock market is something that kids have seen. It goes up and down, it changes. It kind of looks like this, okay? And what investors do, and there's computer models, and that's how when you watch the news, they say buy the stock at this price or sell it at this price. They have an equation, and they look at the equation, they go, well, how much will this be in a certain number of days? How long will it be? And so let's look at that real quick. So if you go to Yahoo Finance, and we look at these, will somebody get that real quick? As we look at these prices, we'll see based on the stock market, if we look at the chart, it goes up and down. That's okay. And so we have the stock market that goes up and down, up and down, up and down. And if you look at it, this almost looks like an absolute value function. This looks like an absolute value function. And so what they do is they make little tiny functions that model the data. And so the goal is to what? Buy something at its lowest price and sell something at its highest price. And they use equations to do that. That's how they predict when is a good time to buy. Now, it's not exact. You can't make things do certain things, but you can guess, right? Notice that when this dips down like this, it's almost symmetrical. When this dips down, it's almost symmetrical. When this dips down, so that's what we use it for in the real world.